Walt Disney's Disneyland.
When you wish upon a star, makes no difference who you are.
Each week as you enter this timeless land, one of these many worlds will open to you. Frontierland. Tall tales and true from the legendary past. Tomorrowland. Promise of things to come. Adventureland. The wonder world of nature's own realm. Fantasyland. The happiest kingdom of them all. Presenting this week,
Ladies and gentlemen, here is your host, Walt Disney.
Thank you, Garco. In this exciting age when everyone seems to be talking about the future possibilities of space travel, there's much speculation on what we will discover when we visit other worlds. Will we find planets with only a low form of vegetable life, or will they be mechanical robots controlled by super intelligent beings? One of the most fascinating fields of modern science deals with the possibility of life on other planets. This is our story.
In the beginning, man's world was his cave. His only concern was for food and companionship. With the sun came the day, bringing warmth and light. With the stars came the night, bringing darkness and fear. Later, when man became a shepherd, he spent more time contemplating the mystery of the stars. Because they moved, he believed them to be living things, possibly the children of the moon breaking away when the moon grew smaller. Then he noticed the reappearance of star formations he had seen before. Where had they come from, and where were they going? An important discovery. The stars fell into the sea. Man's conception of his world had expanded. The earth was an island floating in water, circled by a glittering ring of heavenly objects. As man learned to till the soil, he associated the stars with events of good and evil. When the bull was in the heavens, he planted his crops. This was good. Aquarius, the water carrier, brought the rains. This was also good. With the Virgin of the harvest, the crops were gathered. This was very good. But Draco the dragon brought pestilence and famine. This was evil. Then man began to build cities with towers to bring him closer to the heavens. Man became an astronomer. He sought a more logical explanation for the earth and the heavens above. The earth, he thought, must be flat with its roots deep in celestial waters. In time, he changed the roots to stone pillars to afford easier passage for the stars in their nightly journey. Later, elephants were substituted because of their great strength. To support the elephants, he added a gigantic tortoise who pulled the universe through cosmic waters with infinite slowness. The Egyptians, who loved to draw, represented Earth as a reclining figure with a star-filled sky bending over the top. Shu, the god of air, kept them apart, while the sun and the moon sailed back and forth in a small boat. The Greeks were among the first learned men of astronomy. These great philosophers gave the world many profound conceptions of Earth and space. Plato said, "I have found the Earth to be the perfect shape of a cube, standing in the center of the universe, with all other heavenly bodies scattered round and about." Anaxagoras had this to say, "Being in the center of the universe, the Earth is assailed by the rotating ether, which tears away bits of Earth, flinging them outward, setting them afire, creating stars and planets." Then there was Aristarchus.
Gentlemen, I disagree. The sun is obviously in the center, with the Earth and other planets traveling in circular paths. And thus the sun...
Finally, there was Ptolemy.
Learned men of science, I have listened to all your arguments. I now decree that our great Earth stands immovable as the hub of the universe, the supreme center of intelligent thinking.
Thus, Ptolemy's decree was blindly accepted as the law of science for over 1,000 years. Free and logical thought was stifled by a black period of stupidity, superstition, and sorcery. With the Renaissance came a learned monk, Nicholas Copernicus. He proved mathematically that the Earth was not the center of the universe, but was merely one of many planets circling the glowing sun. In 1610, Galileo published his Sidereus Nuncius, in which he vividly described the wonders of the heavens as seen through that great new invention, the telescope. The planets were not spots of light, but were spheres like the Earth. Jupiter had belts of color. Venus had phases like the moon. Saturn had a gorgeous ring, and Mars was round and red. Today, a space-conscious public avidly consumes tons of story material about life on other planets. Today, as modern science seeks to understand the miracle of creation, it sees an infinite universe, cold and dark, inconceivably vast, without beginning, without end. Across this cosmic void, trillions of island universes move. In one of these, the Milky Way, our sun is but a tiny star among 300 billion other stars or suns. Scientists now estimate that 30 billion of these suns have captive planets. Since the laws of creation appear to be universal, it is almost certain that many of these planets harbor life. Life in the dawn of evolution. Life in the twilight of existence. Life where intelligence may have developed far beyond the stage of man. As an example of how the wonders of life may be evolving with infinite variation on other planets throughout the universe, let us follow the story of our own Earth from its misty beginnings. In the blackness of space, the faint pressure of starlight gradually compresses billions of tiny particles into a tremendous cloud of dust and gas. For millions of years, this cloud contracts with the growing pull of gravity until in the hot, glowing center, the sun is born. Swept into a flattened disk, whirlpools of heavy elements form the planets to circle in permanent orbits around the sun. The Earth begins to cool and shrink, its molten crust pouring out dense clouds of steam and carbon dioxide. In these primeval vapors, the stage of life is set. Steam condenses to rain. For centuries, great torrents of water tear at the rocky face of the Earth, creating the vast oceans. For centuries, rich salts and minerals are washed from the land and carried down to the sea. 1 billion years have passed. Now the warm primordial sea is the cradle of life. Here are gathered all the elements of nature from which life will emerge. One of these elements, found throughout the universe, is carbon, first link in the chain of living things. The carbon atom is unique, for it alone combines with itself and other elements in millions of intricate structures to form the complex molecules of organic compounds. In the slow course of time, some are transformed into proteins, the foundation of all life. These microscopic particles join with other elements to produce millions of delicate combinations. Most are destroyed, but a few of the strongest survive. Now, with time as the main ingredient, evolution of life is inevitable. Eventually, from the complex forces of nature, emerges the first organism, The first living cell. A microscopic speck of jelly able to grow and reproduce with great speed. As the eternal process of change continues, some cells group together in colonies, and from these evolve blue-green algae, the first primitive plants. In shallow pools, the chlorophyll of these plants converts the energy of sunlight into living tissue. For the first time, great quantities of precious oxygen are released, making possible ever higher forms of life. Ages roll by. The first minute cells of animal life appear, dependent on oxygen from the plants to survive. In the millions of centuries that follow, an infinite variety of plant and animal life begins to unfold. Endless adaptation, constant change, infinite variation through inconceivable lengths of time. At last, from the maternal sea, life emerges ready to challenge the hostile forces of a new environment. The pageant of living things spreads across the face of the land. Emerging during the last few seconds in the hour of time is man. Beyond the Earth, at the outer fringe of life's temperature zone, is Mars, the third planet in our solar system where life could exist. Even though scientists think Martian conditions are severe, they believe that if man journeyed to Mars, he could survive here with moderate protection. He would need his own oxygen supply and some sort of protective covering. But life could be almost normal within pressurized houses and pressurized cities. Today, as we face the serious problems of overpopulation and depletion of natural resources, the possibility of Mars becoming a new frontier is of increasing importance in our plans for the future. What evidence do we have that Mars is a planet where life could exist? To answer this, we must search through the archives of astronomy. Here we find that from earliest history, Mars has been an object of great interest.
To the ancients, Mars was only a wandering bright light in the sky. It was the blood-red symbol of war. But to Galileo, the first man to see it through a telescope, Mars appeared as a glowing red disk where sometimes a shadow appeared on one side. As telescopes improved, astronomers began to notice mysterious markings, which they carefully recorded with drawings.
Whether or not there is life on Mars is pure speculation. Before we imagine our neighbor as a planet teeming with super-intelligent beings and exotic plants, let us first consider some of the facts about Mars that astronomers generally agree on. We know that Mars moves in an elliptical path around the sun, and it takes a little less than 2 Earth years to complete the trip. Since Mars travels almost twice as slow as the Earth, we can only observe the planet close up every 2 years. Mars occasionally comes as near as 35 million miles. We know also that Mars is about half the size of Earth, and its gravity is 1/3 as strong. Like the Earth, Mars rotates, and its day is approximately a half hour longer than our own. It has 2 tiny moons which revolve about the planet at great speeds. Also, like the Earth, its axis is tilted, creating the seasons of spring, summer, fall, and winter. With the meager information that has been accumulated over a period of years, astronomers cannot draw too many definite conclusions about Mars. We realize there are probably certain unavoidable errors in our calculations, any one of which could make a big difference as to whether or not there is life as we know it on Mars.
For the past half-century, the intriguing possibility of traveling to Mars in a spaceship has challenged the imagination of many men. Rocket ships of all sizes and shapes have been designed, but most of them rely on an enormous consumption of chemical fuel to escape the pull of the Earth's gravity. A spaceship using an electromagnetic drive to neutralize gravity is the obvious answer, but such a device is still a dream for the future. However, at the present time, an atomic-powered spaceship has been suggested by a leading scientist in the rocket and guided missile field, Dr. Ernst Stuhlinger, who for some years has been working closely with the rocket engineer, Dr. Werner von Braun. This atomic electric spaceship features a revolutionary new principle that will make possible the long trip to Mars with only a small expenditure of fuel. Parts for the spaceship will be brought up to an orbit by conventional chemical fuel rockets. It will then be assembled in the vacuum of space. This unusual ship will be 500 feet across and will carry a small landing craft for the final descent to the Martian surface. Located at the bottom is a small atomic reactor which furnishes a continuous supply of heat. This heat turns silicon oil into steam. After rising up a central pipe, the steam drives a turbo generator which produces electricity to run the ship. The steam is condensed in a giant circular cooler and used over and over again. In the thrust chamber, a platinum grid is electrically charged. The metallic element cesium is vaporized and blown through the white-hot grid. This ionizes the cesium atoms, and they are then electrically blasted out into space at the rate of billions per second. This thrust pushes the ship in the opposite direction. The atomic electric spaceship can operate continuously for a period of years. At the top of the ship, away from the dangerous atomic reactor, is cargo space and quarters for a crew of 20 men. Mounted outside on the thrust chamber assembly is the auxiliary landing craft. When our ship reaches Mars, the landing craft will be released, carrying men and supplies to the planet's surface. A drag chute will gradually slow the landing craft as it streaks into the Martian atmosphere. A few seconds before touching down, the main rocket motors will be fired and the craft will land gently on its nose. Later, the exploration party can return to the mothership by blasting off in the tail section of the landing craft. Here is the plan for our trip to Mars. It will take 13 months and 6 days. Starting 1,000 miles above the Earth, the spaceship will slowly accelerate for 4 months before escaping the Earth's gravity. For the next 7 months, the ship will follow a curved path, finally entering the gravitational field of Mars. An additional 2 months will be spent spiraling into a circular orbit 620 miles above the Martian surface. Here at the space station, our journey begins. The expedition is comprised of 6 ships. Time, a few minutes before departure. Final checks are being completed. At 0 hour, the thrust chambers are fired. We are underway. Our fleet climbs beyond the space station, beginning its outward spiral around the Earth. The speed is increasing steadily. After 4 months and 17 days, 850,000 miles out, the expedition finally escapes the Earth's gravity. At 6 months, 14 days, our speed has increased to 75,000 miles per hour. Mars is steadily increasing in size. The halfway point has been reached. The thrust chambers are reversed. Deceleration begins. The Earth grows smaller. At 7 months, 24 days, crew members witness a spectacular passage of the Earth across the face of the Sun. Three months later, the expedition is 700,000 miles above Mars, and the 45-day spiral in toward the planet is begun. Now, for the first time, the tiny Martian moons Deimos and Phobos are visible to the unaided eye. As we move to within 4,000 miles of Mars, we get a close-up view of the moon Phobos. After 13 months and 6 days, our voyage to Mars is finally completed. The ships are orbiting 620 miles above the surface of the planet. Before exploration begins, test missiles are fired to sample the strange new atmosphere. Now the first landing craft is moved into position to attempt the hazardous 600-mile drop to the Martian surface. This is a crucial moment. Man finally walks upon the sands of Mars, what will confront him in this mysterious new world? Will any of his conceptions of strange and exotic Martian life prove to be true? Will he find the remains of a long-dead civilization? Or will the more conservative opinions of present-day science be borne out with the discovery of a cold and barren planet where only a low form of vegetable life struggles to survive? These questions will be answered by our space pioneers of the future. In solving the enigma of the red planet Mars, man may find a key that opens the first small door to the universe. Carried forward on the wings of modern science, man in the years that follow may discover the miracle of life as it exists in all its countless forms throughout an infinite creation.
working with engineers and scientists, we have found that there are many different opinions as to how we will eventually cross the space frontier. However, there's one point all of them seem to agree upon, and that is whether we use chemical fuels or atomic energy, it will be a rocket-powered ship that will finally take man into space.
We are not exposed to dangers from space owing to the protective layer of our atmosphere. But up there, even the hull of the ship would not shield man against the possible hazards of the mysterious cosmic rays. These tiny bullets from the infinity of space will continually penetrate everything. They may prove to be harmful to man. The most energetic of these atomic rays might feel like stings as they shoot through the body. However, there are other bullets in space that may be of still greater concern. Meteorites. These marauders of space travel at speeds up to 150,000 miles per hour. But if one should puncture the walls of the ship, our air supply would rapidly escape through the opening into the vacuum of outer space. Without protection, man could last not more than 15 seconds before losing consciousness. Also, in the intense radiation of the sun, he would soon broil on the one side and freeze on the other. In the void of space, he will have to wear a space suit. This specially designed outfit must be a flexible, airtight unit carrying sufficient oxygen.
A rocket firing is an awesome demonstration of tremendous power. I think we should find out how it works. One of the best authorities on this subject is the rocket historian Willie Ley. Here Mr. Ley explains the operation of a rocket motor to some of the artists working on the picture.
This is an actual propulsion unit from a V2. And this strange-looking device is both the heart and muscle of a rocket, its motor. Now, all earthbound engines have to burn oxygen from the surrounding atmosphere. But the high-altitude rocket motor has to work in outer space where there is no oxygen. To overcome this, we carry a tank of liquid oxygen here. When burned with a fuel, in this case alcohol, it produces an intensely hot, torch-like flame that would quickly melt the motor. However, we cool the motor by first circulating the alcohol fuel around it, until this fuel finally reaches the point where it is sprayed, along with the oxygen, into the combustion chamber. When this steady flow of alcohol and oxygen is ignited, it produces a continuous explosion which blasts the rocket away in the opposite direction. Here again we have action and reaction. If this motor is placed in a streamlined hull with suitable controls, it can reach a high altitude in a very short time. The V2 rocket motor only operates 65 seconds to a height of 20 miles. But then the V2 has gathered so much speed that it will coast upward to an altitude of 114 miles before gravity begins to pull it back to Earth. Notice that the rocket does not nose over in the thin upper air, but it falls tail first until it re-enters the denser atmosphere where the air, acting on the tail fins, turns the rocket nose down. Early in 1949, space history was made when the payload in the nose of a V2 was a small rocket called the WAC Corporal. When the large V2 reached its maximum speed, the smaller rocket was ignited. This additional boost in speed enabled the WAC Corporal to set a new high-altitude record of 250 miles. This day marked the first time that a man-made object reached outer space. This was accomplished by using a double rocket, then secretly known as Project Bomber. However, we refer to it as a two-step or two-stage rocket.
Is it possible to build a three-stage rocket?
Yes, as a matter of fact, that's the next logical step. Here's a rocket I have designed that has 3 stages. It would stand about 70 feet high or a little taller than the old V2. Here you can see the 3 sections. each one having its own rocket motor. If somebody will please make a sketch for me, perhaps I can explain how it will work. Good. Here we show our rocket in its launching position. The first great blast starts to lift it, and after gaining initial speed, the first section is cast off at 20 miles up. At 45 miles, the second stage is released. The third stage now fires until it reaches an altitude of 70 miles. At this point, our rocket has now attained a tremendous speed and the motor shuts off. Its forward momentum would carry it straight out into space if it were not for the Earth's gravity. This downward pull of gravity bends the upward course of the rocket into a curved path. And if the rocket's speed going away from the Earth creates enough centrifugal force to balance this pull of gravity, our rocket will continue coasting in its curved path around the Earth indefinitely.
Mr. Lay, is there another way we can illustrate this?
Yes, let's explain it this way. If the rocket were to move at a slower speed, the pull of gravity would soon overcome the rocket's momentum and it would return to Earth here. If we add a little more speed, the path of the rocket becomes longer and it goes farther before it returns to Earth here. So if we have our rocket go fast enough, it will eventually follow a curve which matches the curvature of the Earth and will not fall back. We might say that the rocket falls around the Earth as long as it maintains sufficient speed.
But how does it maintain this speed with the motor shut off?
Remember, our rocket is traveling above the atmosphere in space, where there is no air friction to slow it down.
How fast does it have to go to stay up there?
Now that depends on how high we want the rocket to be as it circles the Earth. Let's use the altitude of 1,075 miles. Because at this height, the rocket will have to go nearly 16,000 miles per hour and will make a complete trip around the world every 2 hours. A few adjustments in its course will be necessary, but this can be accomplished from the ground by remote control, after which the rocket will continue to coast freely in space forever.
In other words, the rocket will stay up there just like the moon.
Yes, it will circle the globe as a man-made satellite.
What is the purpose of having this satellite up there?
Having this instrument-carrying rocket moving around the Earth will give us a lot of important information which we'll need before we dare let a man make his first trip into space. To run the scientific apparatus contained in the satellite, a mirror will focus the intense rays of the sun onto a silicon battery, converting solar energy into electricity. There will be a television camera to give pictures of the Earth as it appears from 1,075 miles up. We will collect very important data on the effects of the mysterious cosmic rays. Even hits by meteorites the size of a grain of sand will be recorded. Every 2 hours, when the rocket moves over the North Pole, its radio will transmit a stream of data to a receiving station below. This will be the first outpost in man's conquest of space.